Jai Hind to all. Myself Dr. Nilesh Kumar Gupta. I am working as a professor at Ajay Kumar Garg Engineering College, Ghaziabad, in the Department of Electronics and Communication Engineering. So today I will tell you about the multi-rate digital signal processing. So this title I have taken from unit number 5 of your AKTU subject of digital signal processing. Its AKTU code is KEC 503. So this one title I have taken from unit number 5, that is sampling rate conversion in multi-rate digital signal processing. Earlier you discussed about the digital signal processing, about the digital filters, their realization, their digital filter designing, IIR, FIR, then their Fourier transforms in terms of DFT, then FFT and so on. Now this last unit generally tells about the application part of digital signal processing. What are the real time application of digital signal processing? That tells this unit. So this unit topics are very important if you consider the practical aspects of digital signal processing in real time. Okay. So our lecture title is sampling rate conversion in multi-rate digital signal processing. Okay. So here now sometimes we need at the same time different signals, but we have to communicate simultaneously. How it is possible? It is possible when you communicate those signals at different sampling rates. This is called multiple digital signal processing. So in telecommunication system that transmits and receives different types of signals like teletype, facsimile, speech, video, etc. And there is a requirement to process these various signals at different rates. Different rates means what? Different sampling rates. Okay. So here the multi-rate digital signal processing is required. So practically, because we are not studying, we are not doing this for communicating one signal. Generally we need several signals at a time to process it. Okay. So at that time or at those applications we need what? Multi-rate digital signal processing. Okay. And we need more than one sampling rate is needed for various signals. Okay. So the system that employ multiple sampling rates in the processing of digital signals are called multi-rate digital signal processing system. Okay. There are many cases where multi-rate signal processing is used, like where high quality data acquisition and storage systems, audio and video signal processing, speech processing, transmultiplexer, narrow band filtering and so on. So these are the some applications where you can use this multi-rate signal processing. Okay. Now different sampling rates you can be achieved by using what? Upsampler and downsampler. Because whenever you convert your analog signal into discrete signal, the first process will be sampling. So that sampling you can increase, either you can increase or decrease. So you can increase that sampling rate by using upsampler, and you can decrease your sampling rate by using downsampler. So by this you can increase your sampling frequency, and by this you can decrease your sampling frequency or sampling rate. And this will be possible by using decimation and interpolation. So if downsampling is there, the decimation is called. If upsampling is there, then interpolation is called. So if you are increasing the rate of sampling or sampling rate, so it is called interpolation. That is upsampling. If you want to decrease your sampling rate, okay, or sampling frequency, then it is called downsampling or decimation. That's I am writing in this PPT. Decimation, it means what? It is for reducing the sampling rate. Interpolation is used for the increasing the sampling rate. Okay, that you have to keep in your mind. Now examples. So examples of multirate DSP in signal compression, image coding, space coding, A to D and D to A converter. This is a very important part for digital signal processing, because at the transmitter side always you need A to D converter. At the receiver side always you need D to A converter. Then communication systems and so on. And these are the some advantages that you find whenever you use the multi-rate digital signal processing. What? Less computational requirements, less storage for filter coefficient, less finite in arithmetic effects, less low filter order require low sensitivity to the filter coefficient length. So these are the some advantages that you find in multi-rate digital signal processing. Now this PPT shows about the sampling that you know very well, because whenever you study about the pulse modulation or digital communication, the first step is our what? Only and only sampling. So this is the simple statement of sampling. Whenever you convert your continuous time signal or analog signal into the discrete signal, sampled signal, so that is possible only by the sampling. That you have to keep in your mind always. So what it says, a continuous time signal x of t can be converted into a discrete signal x of nt by sampling it at regular intervals of time with sampling period of time t. And this discrete or sample say x of nt, how it is given by? It is equal to x of t whenever you put t is equal to small n into capital T. So this is just like a statement or the process of sampling theorem whenever you do the sampling. As per the sampling, you know, whenever proper recovery and properly sampling will be there if your sampling frequency is always greater than or equal to twice of fh, twice of fm. Okay, and that is also related with our, if it is equal to twice of fh or twice of fm, so it is called Nyquist rate. Okay, that also you know. Okay, so I am not telling so much here. Okay, because this is the simple sampling step. Now we come on our main, that is sampling rate conversion, because our initial frequency sampling frequency is fs, but now we are increasing or decreasing our sampling rate. So we are converting our sampling rate. That's why I am writing sampling rate conversion. So sampling rate conversion is the process of converting the sequence x of n, which is obtained from the sampling the continuous time signal x of t with a period of t to another sequence y of k obtained from the sampling x of t with a period of capital T. So here a new sequence y of k that you are producing here, it can be obtained how? It can be obtained by first reconstructing our original signal x of t from the sequence small x of n, then sampling the signal with the period of period of time t. So in this diagram it is clear what? Initially you are giving the signal of x of n to D to A converter. Now from this x of n we are recovering the x of small x of t. Then it passes through a low pass filter is having the impulse response of small ht. Now it will go to sampling process through a switch and we generate y of k. So this is the simple you can say block diagram for sampling rate conversion. Sampling rate conversion, it means you are changing, you are converting your sampling frequency from f1 to f2. Either it will be increased or decreased. Okay, that's all. Now decimation. Decimation means what? What I told you, decimation means you are decreasing your sampling frequency, your sampling rate. The process of reducing the sampling rate of a signal without resulting in an aliasing is called decimation. And this is called in simply sampling rate what? Reduction. So, if you are applying a signal x of n of frequency of capital F and it passes through a low pass filter having the what? H of n impulse response. So, you will get the signal Wn of frequency of F, because here only you are passing your signals from through the your low pass filter. You are not doing any decimation and so on. Now, you decimate your signal sampling rate compressor or downsampler. It means here your sampling frequency F is decimated by a factor of m. Now, your new sampling frequency will be F dash is equal to F upon m. So, this is called your decimator, downsampler, that decrease your sampling frequency by rate of m. That is why your new sampling frequency here F dash is equal to original frequency upon m, because you are decimated this original frequency capital F by amount of m. So, this is called our sampling rate compressor or downsampler, and you are reducing your sampling frequency or sampling rate by amount of m. Now, reducing the sampling rate of a discrete time signal is called downsampling. That also I told you. Decreasing means downsampling, means decimation. So, sampling rate of a discrete can be reduced by a factor of d, okay, by taking every dth value of the signal. So, mathematically you can show in simply this one by this block diagram. What? X of n is given here, it will go to the downsampler by d, and y of n is equal to x of dn. So, now your signal here decimated by the dth sampler. So, this is simpler downsampler. You can say this is the simple diagram of downsampler, which decrease your sampling rate or sampling frequency. Decimator is also called subsampler, obviously downsampler and undersampler. So, decimation means what? Sampling rate compression. Why? Compression, why? Because we are decreasing the sampling rate here. That is why we call the compression. Okay. Now, from this example, you have to understand if x of n is given in this way and you have to determine x of 2n. It means under the decimation, the examples based upon the decimation. Okay. That's it. Decimation means you have to decrease your sampling rate or frequency. So, these are your signal. So, x of 2n means x of 2n you have to obtain by keeping every second sample of xn, because d is equal to 2 here. X of 2n, it means d equal to 2, and removing other samples. So, you have to take every second sample. So, here from this every second sample. Okay. So, first this, second. So, second you have to remove. Okay. Then 1 will come, then 3 will come, then 2 will come, then 1 will come, then so on. So, in this way you can obtain x of 2n. So, simple short numericals or examples can be asked in the examination, that if x of n is this, then determine x of 2n, 3n, 4. Similarly, x of 3n, if you need to determine here, you want to determine, again x of 3n obtained by every third sample of xn and removing other sample. So, every third. So, here you can see 1, every third means this. So, 1 will come, then 1, then 1, then so on. So, in this way you can get x of 3n. So, in this way you can determine your decimated signal from your original signal as per the given conditions. Similarly, you can sketch your signal also x of n, x of 2n and 3n as per the got sequences from the xn. If d is equal to 2, then you will get you can get the x of 2n. D is equal to 3, you can get this x of 3n and so on. Now, this is the example or a diagram of decimator, whole decimator. So, in decimator what will happen? So, in decimator at first whenever you give the input signal, it will go to the low pass filter. that is anti-aliasing filter. So at first your signal will go to the filter, you can say decimation filter, anti-aliasing filter and so on. That is having the impulse response of h of n and its frequency response is h of omega. Now you will get the signal of v of n, then it will go to the decimator or downsampler. That down its sampling rate of frequency by amount of d. Now you will get the y of n. So this is the actual block diagram of decimator. So in decimation process this will happen. You need one downsampler and an low pass filter. At first our input signal will go to the filter, that is anti-aliasing filter. Anti-aliasing means that prevents the aliasing in the signal. After that it will be decimated or downsampler by amount of d and you will get the decimated signal. So in decimation always a filter, that is anti-aliasing filter, decimation filter, you can say low pass filter. After that your signal will be decimated by a factor of t. Now what v of n? V of n this. So we know that in discrete time signal x of n is input signal, v of n is output and h of n is impulse response. So v of n is equal to what? What will happen? V n is equal to x n convolution of h n. That is the basic concept of discrete time system. So you can write here v n is equal to what? You can write v of n is what? V of n is equal to x n linear convolution of h n. And by the formula you can write this one, v of n is equal to summation from k 0 to infinity h of k into x of n minus k. Now this v of n signal will go to the downsampler and produce the signal of y of m. So here y of m, okay, you can write here y of m n, okay, you can write, don't worry. So y of n, for y of n is v of md. Now this signal will be h of k into x of md minus k. So simply at first your signal will go to your low pass filter, anti-aliasing filter, simply convolution will be there, you will get the signal, and after getting this signal it will go to the downsampler and finally you will get the output signal y of m. Now decimation. Decimation means the process of reducing the sampling rate. Again I am saying, I am telling you, let m be the factor. So m is equal to t dash by t. T dash is what? It is new sampling time, t is original sampling time. Like sampling frequency fs, fs dash. Similarly sampling time will be there, f is equal to 1 upon t. So m is equal to, you can write t dash by t. So signal is decimated by factor of m. So here in decimation f dash is equal to 1 upon t dash and m is equal to f upon f dash, okay, and f dash is equal to f upon m. So these are the small and simple formulas. Sometimes you need this one, that is why I am telling you. So new sampling rate, new sampling frequency under the decimation, you can find out these by using these formulas. Similarly interpolation, interpolation means what? It is upsampling. Increasing the sampling rate of a discrete time signal is called upsampling. The sampling rate of a discrete time signal can be increased by a factor of I and placing I minus 1 equally spaced 0 between the each pair of samples. And you can show normally by the mathematical expression for upsampler. Y of n is equal to x n upon I, where small n is equal to 0 plus minus I plus minus 2i and so otherwise it will be 0. Now similarly upsampling, you can see here the examples. X of n, you are giving the signal of x of n, it is simply interpolated upsampled by amount of I and you will get output signal of y of n. If your x of n is equal to 1, 2, 3, this is the example that is given in the question. So if you want x n by 2, it means you have to add I minus 1, n by 2 means I is equal to 2. So you have to add I minus 1 sum, okay. So, I minus 1, 2 minus 1. One sample you have to add every second. So, 1 after 1 you are adding 0. Then 2 after 2 you are adding 0. 0 you can add, because here you are increasing the rate of sampling. So, because this is for upsampling factor for I is equal to 2. Similarly, n is equal to I is equal to 3, x n upon 3. So, n upon 3, I is equal to 3, it means 3 minus 1, 3 minus 1 minus 2, it means you have to add 2 samples. You have to add 2 samples. Okay. So, 1 after the 1 you have to add 2 samples. After 2 you have to add 2 samples. Simple. So, this is for upsampling factor of I is equal to 3. Similarly, you can sketch your signal here, okay, for I is equal to 2 and 3 and so on. And this is the diagram of block diagram of interpolator. Earlier I told you the block diagram of decimator. This is the block diagram of interpolator. Interpolator means what will happen? Input signal you are giving here. So, in this interpolation, firstly you upsample your signal. After that it will go to the filter. In decimation, at first you have to give your input signal at first to the filter. After the filtering it will go to decimator. In this reverse. Initially, if you are giving the input signal of x of n of frequency f input, so it will go to the upsampler. So, initially its sampling rate increased by the upsampler. Then this upsampler will go to the interpolation filter and you will get the output signal of frequency f0 and output signal y of n. So, here it is called interpolation filter. So, this interpolation filter is having the transfer function Hz is called here anti-imaging filter. Anti-imaging means that type of filter that prevents unwanted images in the signal. Anti-imaging, that in decimation that was anti-aliasing, that prevents aliasing, here anti-imaging filter, okay, and that always applied after the interpolation, that you have to keep in mind. In decimation, initially filter, we have to filter the signal, after that decimation will be there, but here the reverse process is, okay, that you have to keep in your mind. Now, similarly for interpolation, T dash by T is equal to 1 upon I, F dash is equal to 1 upon T dash and F dash. So, this is again like decimation. Now, your frequency is increased here. So, F dash is equal to I into F, I into F, okay. So, now your frequency increased by the factor of I, that you should know, okay. So, this is the our interpolation. Now, what I told you that I am writing this PPT, usually an anti-imaging filter is to be kept after the upsampler to remove the unwanted images developed due to the upsampler. The anti-imaging filter, the upsampler, both together is called interpolator. Interpolation is the process of increasing the sampling rate by integer factor of I by interpolating I minus 1 new samples between the successive samples. If I is equal to 3, then you have to add 2 samples between the successive samples. If I is equal to 4, so you have to add 3 samples between the successive. That is the basic concept of interpolation, that you have to keep in your mind, okay. Then it will be better to all of you, okay. Now, this is the again I am showing the PPT here, the fundamental multi-rate operation like decimation and interpolation. So, this is what in decimation, what will happen? Filter, then M-fold estimate. In this L-fold expander or upsampler, then filter. So, similarly similar concept I am trying to understand you from this PPT. Now sampling rate conversion by I upon D. I upon D means what? That we have to apply here interpolation, decimation both. Okay. Because generally we want somewhere some high sampling rate frequency, somewhere we need low frequency sampling rate frequency. So I and D, interpolation, decimation, both we need. That's fine. So this is the one example that I am showing in this PPT. Now sampling rate conversion by factor I upon D. A sampling rate conversion I upon D can be achieved by first performing the, if you want to achieve I upon D, so then what will happen? So it can be achieved by first performing the interpolation by factor I, then perform decimation. If simultaneously you need I and D both, so firstly you need interpolation. After interpolation you have to apply decimation. Always remember it. What? Performing firstly what? Interpolation by factor I, then performing decimation by factor D. Okay. That you have to keep. It consists of cascade configuration of interpolator and decimator. It means in interpolator what? Anti-imaging filter you need. In decimation you need anti-aliasing filter of having H1K and H2K response of the filter operating at the sampling rate. Hence, it can be replaced by simple low pass filter with transfer function H of Z. If you apply simultaneously at a time anti-imaging and anti-aliasing filter, and finally you can combine these two filters by response of H of Z, that I am writing here. Now, if the sampling rate is to be converted by factor of m by L, okay, decimation and interpolation, then again our new sampling time and new sampling frequency will change, and the relation between this T dash by T is equal to m by L or f dash by f is equal to, what will happen? This, if T dash upon T m upon L, so it will be L by m. Or if you determine f dash, so it will be L by m into f. So by these simple formulas you can calculate your new sampling frequency and new sampling time interval easily. But always you have to keep in your mind what? That interpolation always precedes the decimation. Okay, that you have to keep in mind. Now this is the diagram. From this diagram it is clear to you that interpolation precedes the decimation. So in this diagram you can see x of n, you are giving the input signal x of n, it will be interpolated by amount of L, then you are using the filter of H1K, impulse response. This filter what? This is your what? Anti-imaging filter, okay, under the interpolation. This is your interpolation. Now you will get some signal of Y1K, it will go to the decimator. In decimator at first it will go to the H2K response of filter. Then your signal decimated by factor of m, and your final frequency f dash is equal to what? That I was writing in last PPT, L by m into f. And this filter is what? This is your what? Anti-aliasing filter. So in this way interpolation precedes the decimation if you apply I by D factor sampling rate conversion. Okay. Now this is the what? Cascade connection of I and D. Now these two different low pass filter H1K, H2K you are using here, and it can be combined by the single filter of response of H of K or H of N. Then what will happen? Okay. So if this is, then you can replace the simple interpolation and this filter, you are combining H1K and H2K, and you are combining and you are making one composite filter, and you will get the answer. So you can also use, or generally use, 5 मिनट और लूंगा, कितने हो गए अभी? हाँ 35 हो गए, 5 मिनट और लूंगा, है ना? अब बंद कर दूंगा अपने आप। हाँ मैं समझ गया, ठीक 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 है, ठीक, ये आएगा तो नहीं ना? ठीक ठीक है, ठीक जी, ठीक है, ठीक. So in this way we can use cascade configuration of two filters, and those two filters can be combined into the single filter. Okay. And you can achieve interpolation decimation both. But you have to remember, always you have to keep your mind, remember it, what? Interpolation precedes decimation. At first you have to do interpolation, after that decimation will be there. Okay. And now multi-stage implementation of sampling rate. Multi-stage means what? If you want to apply several stages of decimation and interpolation. So in stage 1 you are decimating, so stage 2, stage 3 and so on. Similarly, multi-stage interpolator you can use stage 1, interpolator 1, interpolator 2 and so on. Okay, so if you want to increase or decrease the sampling frequencies or rate by the high amount, then you can use multi-stage implementation. Multi-stage implementation of sampling rate conversion, either using the multi-stage decimator or multi-stage interpolator. Now, multi-stage, if you are applying multi-stage structure, so less computation you require, storage space will be less, and filter design problem will be simple and so on. So these are the some advantages and reason behind the using multi-stage structure. But demerits or limitation of system also will be there, but that proper control structure you need for implementing the these multi-stage structure. Application of multi-rate DSP. So if we go the application part, so these are the application: design of phase filters, interfacing of digital system with different sampling rates, implementation of narrow band low pass filter, digital filter banks, sub band coding of speech signal, quadrature mirror filter, trans multiplexer, oversampling A to D and D to A. And I am highlighting these two. These two are very important. What? Sub band coding of speech signal and quadrature mirror filter. Very speech signal. What we are seeing here, we are discussing here, digital signal processing. So generally we are processing our speech signal. So sub band coding is very important, because in our speech there are so many components at higher range, at lower range, and can be occupied by low pass filters and high pass filters. Then sub band coding is very necessary and important for speech signal processing. And then the concept of quadrature mirror filter and filter bank will come. So that's why I am highlighting this. Okay, so there are so many terms for this: analysis, filter bank, synthesis, filter bank and so on. So this is from my side about this title, sampling rate conversion in multi-rate digital signal processing. So now I finish my talk here. If you have any query or any question, you can mail me on my college email ID. Okay, guptanilesh@akgec.ac.in. One thing I am telling you, this is totally numerical paper, and this wants only your practice. Teacher only can tell you about the process, steps, solutions and so on. But practice is very important. If you do the practice, this subject is very good. Very good subject, and that will be very beneficial to all of you also. Scoring subject also. Okay. So always do practice and practice in this subject. Okay. And the book for this subject, generally John G. Prokes. This is the, you have to refer Prokes book by Digital Signal Processing, Sahali Vahanan, then Open Schiffer, Johnson and Johnson, and so on. So many books are there. But you have to do practice and practice for solving the numericals, examples, derivations, and so on. Especially the practice on partial fraction and factorization. That will come in each unit. So, thank you very much. This is from my side. All the best and Jai Hind to all.